dia, boa tarde, boa noite aos internautas que nos acompanham neste programa Nanoalerta N.174. Uma série de programas dedicados ao campo especialista, para as pesquisas sobre nanotecnologia realizadas no Brasil. Também fazemos este programa porque é aqui que nós podemos discutir os impactos da tecnologia na sociedade, no meio ambiente, na economia, na ética, na saúde, coisa que não são discutidas onde se faz nanotecnologia no Brasil. Por fim, fazemos diretor do Instituto NANOSYSTE na Universidade da Califórnia. Eu fazer Okay, Paul, would you please introduce yourself?
Yes. So I'm Paul Weiss. I'm a nanoscientist at UCLA, University of California, Los Angeles, as you heard. My training was in chemistry and physics, and I later branched out into engineering, medicine, neuroscience, and other areas, as we'll discuss during the hour. First, thank you very much for having me on the show here, and also I'm sorry I didn't make it to the Brazilian NOS this week because of Hurricane Irma. But very much like this morning, last Tuesday, very early, actually an hour and a half earlier, I gave my lecture by Skype. So I'm looking forward to having a discussion and look forward to hearing what you have to say.
Okay, maybe you can start in general aspects about the nanotechnology in medicine.
Yes.
Development in this area.
Very good. So from a general perspective, let's start that way. The big advantage of nanoscience is that it's the scale of function for biology. My wife is a neuroscientist, excuse me, and she likes to say the brain has always been nano, but nanoscientists are just some millions of years behind. And so we have this very great advantage that where we control and where we measure is one of the most interesting scales, at least in biology. Think of a virus as a complicated yet precise nanoparticle. It might be tens or 100 or so nanometers across. It has coding both inside and outside in terms of its protein shell and its nucleic acid inside, and it's able to interact with other biological systems in order to reproduce. In my own case, how I came into this world is as follows. What we're best known for in our laboratory is looking at the ultimate limits of miniaturization, the smallest switches and motors in the world, where we can look at a single molecule or assembly that functions as a switch that changes state, for instance, and we can stimulate that in a number of different ways. But in order to do those measurements, we had to develop two capabilities. The first was to place individual chemical functionality, so part of a molecule or a molecular assembly, into a controlled environment, and then we had to develop microscopes that could measure structure, function, and spectra all at the same time. And so both of those capabilities played into our work in biology and medicine. When my wife and I first got together, we were actually colleagues, and she wanted a way to place neurotransmitters on surfaces so that she could capture proteins from the brain involved in neurotransmission and so that she could develop artificial receptors to turn around and put in the brain to understand what a thought is and what a memory is. That, with that help, later became the BRAIN Initiative under President Obama. Another key event for me was moving from Penn State to UCLA 8 years ago, when medicine, science, and engineering are all proximate. And so now we have very strong interactions in medicine, and we look at where our capabilities and new ones that we develop can possibly, and already in some cases have been able to have impact in medicine. And more recently, I've put together within my group an oncology group to look at how we can use advances in nanotechnology to put gene editing payloads into cells for the treatment of cancers, blood diseases, immune diseases, and so forth. So really, I think there are two key parts for nano in medicine. The first is the technological one, in that we're matching the scale of function. The second is something a little more, a little different, and that is the field of nanoscience and of nanotechnology has developed because we've learned to talk to each other across different fields. And while that might have been useful in other fields to develop, for some reason it did not. And so the people who've been drawn to this field are interested in each other's problems and ultimately start to look at how they can help, what capabilities they can add in order to address what are often refractory problems. And so for that reason, we've been able to make, I think, more rapid advances in medicine in nano than other fields that have been more isolated.
Okay. General question.
Yes.
To do one research about this subject that you show for us, how much money we need? How much time?
Yes. It really depends upon the problem, of course. So for the brain measurements that we're really now just getting started on, Aaron Millar, who's the editor of ACS Chemical Neuroscience, has been working perhaps 20 years, and we've been working 15 together. And we're now just at the point where we have those artificial receptors put into sensor arrays. And I took every penny we could scrape together from our move from Penn State to UCLA, as well as any unrestricted funds we have, and then finally also some federal funding. So that was a fairly substantial effort, as well as a lot of expertise of many people. For the stem cell work we've done, it's taken many people identifying the problems, but then many ideas have worked very rapidly. Again, it takes some effort in terms of microfluidics, in terms of nanofabrication, and so that's been something we've been able to put together very rapidly just in the last few months, but it's also, of course, taken some capabilities. As you mentioned in the introduction, I used to be the director of the California Nanosystems Institute. I think many universities or countries have these user facilities that generally cannot pay for themselves. We need some support in order to participate in the field. And so over several years, we put together many capabilities that became available not just to our faculty and students, but to others around the world. Those are both costly, and one needs to keep them up to date. Technologies advance quite rapidly, and if you don't have the most current technologies, then you're not able to do things that people in other places are. So that's sort of the bad news. The good news is, we happily play with others. We have visitors from around the world. Just in my own laboratory, I usually have about 8 international faculty at any given year, and so that gives collaborators around the world opportunities to work with the tools that are both available generally as a user facility and also to the special ones, the special capabilities that we develop in our own laboratory.
Okay. Do you think in general, for the nanotechnology, until now, we have so many promise, so many hype, or reality is okay?
Well, sure, there's plenty of hype, right? We've read plenty of magazine articles and journal articles where the journals are really magazines pretending to be journals, where cancer's been cured many times, all of our other problems have been solved, we've solved the energy problem. There's a lot of that. And one of the interesting discussions we had last month at a meeting with the NanoSystem directors from around the world was, how do we get past that and give realistic expectations for what we want to and can do. In medicine in particular, rather than be difficult to make a complex package get through regulation. Let me be a little more specific in that. So the dream is we make a nanoparticle or nanoassembly that goes to the right place in the body to target a tumor or organ. It stays there, it knows it's there, it releases its payload, and it tells us that it's been effective. In reality, if we put together such a package, it would be difficult to work through the regulation necessary to make it available to humans. In practice, what we have available to us is we know that the blood vessels in tumors are a little bit leaky, so if you put things of approximately the right size, they'll get stuck there, and we know the tumors are a little bit more acidic, and so if we use some of the ideas from nanolithography of using acids to change assemblies, then we can make the payload delivered more effectively. But we don't have an idea, for instance, we don't have a good way now of placing chemical functionality around the outside of that assembly in ways that we do know how to do when we look at, for instance, flat surfaces. So there's some simple successes, right? Abraxane is sorry for some background noise there. I'll try and talk a little louder. Abraxane is it's a protein nanoparticle with the leading anti-cancer drug, Taxol, in it. The efficacy is about the same, but the side effects are much reduced. And so in that way, people having to undergo that chemotherapy are both less uncomfortable, but in fact, since they're already compromised, they're more likely to survive that treatment. And so about a third, as I understand it, a third of the Taxol delivered, a third of the prescriptions for Taxol in the world involve that very simple nanoassembly.
Okay, you use the word nanofabrication.
Yes.
Yes. Nanofabrication is direct with nanomedicine.
Can be. So nanofabrication has really been advanced largely by the semiconductor industry. We have these semiconductor foundries all over the world that produce the chips that are in our computers and smartphones and cars and other devices. And so that idea of sculpting from the top down, right, that it's essentially a descendant of stone and wood carving we've done for centuries, that has now been advanced where the factories at which that are done cost upwards of billions of dollars. And so that part of it can be useful, for instance, in making sensing devices that we can use in nanomedicine. There's another approach to nanofabrication that is going from the bottom up, essentially from molecules up to nanoassemblies, and that's in some ways a derivative of chemistry and polymer and material science, and those are, I would say, less equipment intensive methodologies, but still I would say qualify as nanofabrication. And when we want to put together those precise assemblies to interact with biological systems or parts of our bodies, I would term that as part of nanofabrication as well. One of the things that is required for each is a set of tools that lets us measure what it is we've made, so that we can do so reproducibly, so we can tell when there's a change, and so we can do systematic modifications to see when we've been able to make something successfully and test its use.
The other part of the nanomedicine that not use the nanofabrication, what is?
So there are certainly tests that we want to be able to do. For instance, for early diagnosis of disease. There are many diseases, if you catch them early, you can do something about them. And so you don't necessarily need nanofabrication to make such a device. You just have to come up with a clever way to sense the presence of the disease at in a place and with sufficient sensitivity to tell you reliably that you have it or you do not. In some cases, we also want to do things, as I described earlier, where you take a stem cell and you convert it to something that can repair or replace something wrong in a patient. For instance, in blood diseases like sickle cell anemia, we know what the genetics are that lead to problems with those patients, and if we can replace the DNA in cells that we can get into the bone marrow of the patient, then their blood will be restored to having the full oxygen carrying capacity that people without that disease have. And so essentially that would give us a cure if we can manage that. But it's really a mixture of nanotechnology, biology, and medicine in order to make that dream a reality.
About the security.
Yes.
That the level of security in nanomedicine now is good.
So one of the other considerations in the field is safe by design. We try to, so right now in America, we find that nanomaterials are treated like new chemicals, but there are so many possibilities that it makes no sense to do testing of nanomaterials the way we would do with a new chemical, because there aren't enough animals, nor enough money in the world to do that testing. And so what we've been advocating is looking at collections of materials to try to assess, okay, is this class of materials ready for commercialization, not just in nanomedicine, but in general deployment? And if so, let's go ahead and move forward with those. In some other class of materials, there may be something that puts up a warning flag, in which case we need to do more systematic and precise measurements of both the material's properties and the safety properties. When we do those tests, it turns out not all the effects are bad. When we see something positive, we can also take those biological effects and try and apply them in medicine. So on the side of general materials, I think that internationally those ideas are very much embedded in the community, and we are moving forward. In terms of nanomedicine, the progress is very slow, in part because of the very strict regulation in terms of what we can deploy in the clinic. So there's a terrific article by Mark Davis, who was at Caltech, is now moving to USC, on what it took to get a potential nanomedicine approved. And he worked backwards to make the assembly as simple as possible so that it would get the easiest approval. And even so, when we went to the U.S. Food and Drug Administration, FDA, it took 61 volumes of data in order to apply for approval. So when we talk about making something much fancier or more complicated, it's going to be difficult to get that kind of approval, and essentially we do need to think about how to simplify the materials we're making to basic components that we know will be safe in medicine.
And do you think that the framework, theoretical framework for the nanotoxicology is okay?
Oh, I think we have a... Can you still hear me? You dropped out a little bit there. Oh yeah, okay, very good. You dropped out for a moment there, but I think you said is the theoretical framework for nanotoxicology okay? And I think there's a long way to go because we don't have all the experimental data either, so those two are being developed simultaneously. We're still trying to understand what the key biological networks are with which nanomaterials interact, and as we do that, theory and simulation will come along. Hopefully, as in many other areas of nanoscience and nanotechnology, theory will also help lead and will ultimately get us to the point where it will tell us where to explore experimentally, but I haven't seen that happening yet.
My question is because here in Brazil, we have university money with public money.
Right.
And the public money is used, the majority, to produce new knowledge for new products or processes.
Yes.
Not for the impact.
Mm-hmm.
So we have a gap, a very long gap between the new knowledges from nanotechnology for new products, in the other side the impact. I think in the United States it's not similar, but also problematic also. Because if you, I read some time ago one paper about this, where is the gap in the development of nanotechnology in the United States research? So the gap was so big also for the part of impact. What is your opinion?
Yeah, so there's a very big range from basic research all the way to application in products. And what we find generally, not just in nano, is there's a very big concentration of people doing curiosity-driven research, and there are companies and startups included in that group that do product development. In between can be difficult. We and others around the world try and put in their words to make a bridge, and it's become easier in the United States with the change in laws over the last several decades to develop a technology out of the basic research lab, such as a university, in order to move it along far enough either to make it into a real company or to have it picked up by a company. But I would say there are two things both Brazil and the United States have going for them, and that is a long tradition of scholarship. I find that in Brazil, even though resources may be limited, there's intense interest still in the science, and that is what opens up new fields. I won't say it's independent of resources, because the resources are important, but that's what will keep Brazilian science moving forward. And in terms of nanomedicine, that seems to be one area, at least in my experience with Brazilian scientists, where there's still very much forward motion. So many scientists who may not have been in the area of nanomedicine have moved in that direction direction in Brazil because there are still resources available, because clinical collaborators tend to have some resources available to them, and so in a sense the financial crisis in Brazil has moved forward has helped to some extent in nanomedicine. In the U.S. And many places in the world, there's often a separation between medicine and other areas of science and engineering. Part of the draw of us to move to UCLA is science, engineering, and medicine and nanoscience are all right next to each other, and so we work very closely together every day. I think there are only a few places in the world with that kind of advantage. In Brazil, the nanoscience community is not so large, and so you also have that frequent interaction between medicine, science, and engineering. At least when I go to meetings, that's what I see. I haven't spent much time at universities there yet, although I'm looking forward to that on a return trip.
You think that nanomedicine can help to legitimize the nanotechnology in general?
Well, I think everybody wants to see, after more than a decade of substantial investment in nano, what the products have been. But I don't think we will often see a product where you say, this is nano. I think more often what we'll see is there's nano inside this. And so it's important for us as a field to identify that our computers and our phones and our sunscreen and our paints and many other our sensors in hospitals and so forth all come from nanoscience and nanotechnology now. And so we'll, maybe not at all in hospitals yet, but we're getting there. So I think it'll be important for us to identify to the public, who after all are the ones who support our work, what it is we're doing for the world. That said, the field is still very young. We're still making discoveries of new materials and new properties that have tremendous opportunities for the future, but may not be ready to commercialize yet. And so, just like we said, there's a spectrum from basic science to products. We want to keep moving that whole spectrum forward and continue to do basic science and make new discoveries. At the same time, we're developing those processes, materials, medicines, diagnostics, and trying to get them into use by the public, including and especially in medicine.
Okay, you can show for us some examples that we will have in the near future. Products
Sure.
from non-medicine, and the
Yes.
other products that we will have in the middle future.
Sure. So I have one that spans both of those. I had a chance to meet many dentists in Brazil, it turns out. So we have 200 or 300 species of bacteria that live in our mouths. Some of them give us cavities, some of them give us root cavities, and some of them, if we have an implant, they'll eat around the implant and the implant will fall out. So for that latter category, periodontists know this, but they have no way to measure the existence of those bacteria. And so if we developed a simple test that let us say, oh, we have that species, we better not get that implant until we clean that species out of our mouth, then the patients who suffered that implant falling out would be much safer. So we don't have that detection capability yet. It's something that would have impact on a significant number of people and would change that field of dentistry in a very positive way. There is some basic science development that's necessary, some development of a product, and then I would hope fairly quickly we could turn that into something that's in common use around the world. I would say that spans both the should happen very quickly and isn't there yet in any sense of detection.
Yes, in a near, in a middle field.
Yeah.
We will have from the non-medicine.
Right, so that should be, we can imagine taking that one measurement and applying that across a broad range. We have many, just in terms of studying the microbiome that we have in the mouths and our skin, in our gut and so forth, those on that middle future that you're describing, I anticipate that we'll have many more tools to assess and understand where we are. Right now we only have the information to know what a healthy ecosystem is in and on us, not to mention, in the earth, in the ocean, and in the air, which also have their own populations. It's something that you would not necessarily think at first glance is an important area for nanoscience, but in fact I anticipate both the tools for that set of studies and the community that can bring together the necessary scientists, engineers, and clinicians, and physician scientists, in order to create what we need in order to do those measurements. I anticipate all that will come from nanoscience. And I can send a link to your viewers if you like. We wrote a roadmap for that area a couple of years ago before the U.S. announcement of the Microbiome Initiative, but there will be other such initiatives around the world. It's an area where there is not a high cost of entry, and so even when budgets are low, there are opportunities to study, to study those systems locally.
Okay, and do you believe that the nanomedicine and the enhancement of the body will have some social problems because
Enhancement of us?
the body, our body?
Oh, yeah. I don't think we know how to do that. I mean, we know how to correct parts, and so if we could, for instance, develop ways to preserve our memory or preserve our sight or hearing, that would be a good start. I don't think we have a way currently to give any significant enhancement in any area. There are ways that we try to interact with our brains. For instance, if we've lost the ability to control an arm or a leg, that could involve nano, but that's not really enhancement, that's more repair. I'm not saying enhancement on the horizon, nor do I see a lot of people working in that area.
Do you believe in the future here?
So my specialty, as I mentioned at the start, is motion at the nanoscale. And what we can do with moving a molecule or a nanoassembly is very, very far from what science fiction writers attribute to us. And one of the most important things in reaching the public is making clear that what it is we're trying to do and how. So we're just barely able to make something move like this, a fraction of a nanometer. There are biological viruses, for instance, that know how to move and interact and so forth, but that isn't a capability we as humans have been able to develop. There are times when it would be useful, for instance, to have something that went through a barrier, either in a tumor or to get in the brain. There's an example of African sleeping sickness. The parasite that causes that has a tail that lets it move through the body, and when it gets to the brain, it turns the tail around and uses it as a drill. Now, we have a lot of trouble addressing diseases of the brain, and we don't have good ways to get across the barrier between blood vessels in the brain, could we possibly co-opt something like that, use a hybrid between a biological system and a nanosystem? Again, maybe, but we're not really there yet. Right now, we have only simple objects that can move relatively slowly, and usually the fuel that we use is not something that we find in the body. There are now a few examples of where people are trying to use stomach acid, for instance, to help a little object move, but generally the speed of motion tends to be slower than the flow of fluids through us. So we're a long way from nanorobots at this point.
You don't use the expression download the brain.
No, I don't.
You believe this?
We're a long way from anything like that. Yeah.
Because I saw yesterday in the TV and one startup company are investigating
I see.
how to do the download of the brain, to put the brain, our brain, my brain, in the robot.
So you're right, I have a very poor memory, so I could certainly use a backup if someone can come up with a way to do that, but I don't see that as something we know how to do. We can't really tell what people are thinking yet. We can identify places where there is activity in the brain, and sometimes we know how to stimulate those, and in some ways we know how to control activity at a global level across different bands of frequency to use our brain activity to control something like a mouse on a computer or a trackpad. But that's really the level at which I understand our current knowledge and ability to measure the brain are.
You think that
We don't know. I'll continue just 1 second. You know, at the cellular and neural circuit level, we still don't know what a thought is and what a memory is. And so part of the brand initiative that we have put together is designed to do just that. We don't know what happens if we stimulate in one place, whether chemically or electrically, what the result is within the neural circuit. And so the idea that we could then go in and read the brain, we know the basics, the basics of logic and memory within it, that's a little silly.
do you think that the advance from the nanomedicine will be able for all people, or only a few people will have access to that kind of technology?
That is an excellent question. And that really depends upon the design. So, for instance, right now stem cell treatments in the U.S. for an experiment using viral infection of the cells, the experiment costs about $65,000, and treatment for patients costs more like $300,000. And so that is out of the range of most people. One of the developments we're trying to put together is a much simpler way to do that, where the cost would be perhaps 1,000 times lower, and that would become accessible not just at special hospitals like UCLA, but also around the world as a way to treat and cure diseases rather than, I would say cure diseases rather than have to, either have people pass away or need treatment their entire lives, which can be very expensive. So part of it is design of the experiments, and part of it is, what will we find as possible. So, for the developed world, there are a few cases where we've been very lucky to figure out the genetics of diseases and treat treatments have become available to a small number of people, but expanding that and making those treatments and cures generally accessible is an additional constraint and challenge to the scientists, engineers, and clinicians who are developing those. For me, who wouldn't want to treat people around the world instead of a few people at special centers? And so we design our experiments such that we'll have the broadest application possible.
Okay, you think that the
Right. I mean, we are continually discovering new materials and properties, and so we may find others that are useful in medicine or in other areas. It's all part of the process. At the front end, we have discoveries, and then we have elaboration and understanding of what those materials and properties are. And as we determine them, we're able to say, oh, well, we'll make this material or this property apply. And so I think it's likely that some of the new discoveries will ultimately end up in medicine, but because these are really experiments, it's hard to predict just what will happen.
if you have materials
For metals? Oh, it just depends upon the metal and how stable the material is. Sometimes even a metal that on its own would be toxic, we can encapsulate it and keep it from interacting directly with the body parts inside. So for instance, in enhancing contrast in magnetic resonance imaging, we encapsulate rare earths, those ions that are down at the bottom of the periodic table. We can use those, and we can keep them from direct interaction by packaging them up in a stable structure such that they're not released. In other cases, there are materials that are completely compatible with us. A common material that we use is silica, silicon dioxide, because our cells and our bodies are very tolerant of that material. It slowly dissolves and so forth. And so it's really a design problem. You might have a look at John Rogers near Northwestern from Illinois, who would make digestible electronics, where all the pieces of it, including the metal traces, were dissolvable and non-toxic. And so over time, they would have function, and then they would just dissolve into our bodies safely. So it's certainly possible to design structures that are safe in that way.
Do you think that if you have a good design, you will not have important problems in the future for the use for non-existent?
Well, I think that safety by design aspect is very important. And so we've put together a series of components that we believe are safe, and it's important for us to be able to expand that series so that we have more components that we can use to advantage. When we have something that's a treatment, usually since it's toxic to a parasite or to a tumor within us, for instance, chemotherapy is always a race between killing the cancer and killing the patient. And so sometimes it is valuable to use something that has some toxicity to us, but one of the potential advantages of nanomedicine is targeting it to the place or the object or the organ or to the cells that we want to eliminate, and reducing the effect that it has on us. The rest of us.
Yes, and the importance of the industry of medicine. What is your opinion? What is stage we have now?
Oh, we're very, very early. We're really just at the very beginning of what we can do. We know from biological examples that there are tremendous possibilities and capabilities in the nano world. Just look at the very wide range of viruses that we started, where we started our discussion. Viruses can do so many amazing things, and those are simply nano objects. They have coding on the outside to control interactions, to control capture, and inside they have programmed code of DNA or RNA that is able to elicit a significant response from the host cells. And so, in advance to where we imagine nanomedicine can go, that's an opportunity to correct our own DNA or to turn on or off signaling within cells if we do this correctly. So I think we're nowhere near what nature has put together so far. We're just learning some of the rules now of interactions, targeting, stability, safety, design, and so forth. So I think there's a very big future ahead for nanomedicine.
The companies that are working in non-medicine are the same that is working in medicine in general, the same multinational, big industry or not. Non-medicine is still income.
I think for now, most of the developments are being done in small companies, and then when there's success, those are acquired by larger companies. I wouldn't necessarily know what's going on at the largest pharmaceutical companies, but I don't see a lot of activity in terms of publications there. I see university labs and other government labs where there are small companies where there are advances, and when those become successful or close to successful, then the big companies have been eating them up. So, for instance, a vaccine was started in a small company by one of our former faculty, Patrick Soon-Chung, who sold the company to Celgene for $3.5 billion.
Maybe in the future, the biggest companies buy the startups.
I think that's the most common. That's most common right now, at least from what I've seen from a limited perspective. I think that's right, that there's acquisition of startup companies that have shown some success.
So I put many questions for you, but non-medicine is so big.
Right.
So
Hopefully getting
if you
bigger.
have another aspect to show for us, maybe you can show.
Yeah. So in fact, there's a very big challenge and barrier relative to getting therapeutics into humans in the clinic. But diagnostics, I would encourage your listeners to pay attention to diagnostics as well. Those can be easier. You don't necessarily have to go into the body. You can use spit or blood or urine or dabbing on the skin. There are opportunities there. There are certainly scientists and engineers in Brazil who have capabilities to move into that area. There are tremendous needs for looking, for instance, for parasites, for infection, for safe water, air. All of those are very big opportunities for nanomedicine that may require less substantial investment, and the impact may be even greater in that you can reach a larger population. And so I see that area of diagnostics. Sometimes when people think of nanomedicine, they forget about that. But I see very big opportunities there for our community, and I would say keep an eye out there. Yeah.
You believe that he will have our individual label chip?
Could be. Maybe in our toothbrush. So you can see what's in our mouth, for instance, but then you have to not show your toothbrush. But right, it's certainly possible that we could do regular assays of our health and of our microbiome if we could come up with simple tests. Or as I said, there may be some specialized cases where it's important to do so. For instance, we're about to have a procedure in our mouth. We should check regularly before that to see that it is safe to go ahead. And we can translate those ideas over into other organs as well.
Okay, Paul. Thank you so much for your contribution, for our talk, talking about numbers, that is so big area of research. Now we have some more information about this.
Thank you so much for having me, for reaching out, and also for meeting me in the Sao Paulo airport on my last pass through. Sorry not to have been in Brazil in person this week, but I look forward to the next opportunity. Thanks so much, and goodbye to your listeners.
Okay, bye-bye.
Bye-bye.